We have a view here of Huascaran. This is the highest tropical mountain on Earth. It's also one of our drill sites. And this is in Cordillera Blanca in north central Peru. And I want to acknowledge my co-workers and graduate students who have worked over the years on this particular endeavor. And also our funding agents, which are very important for this type of work. If you go downstairs here at the Byrd Polar Research Center, you'll see both clean rooms, and here on this floor we have mass spectrometers that are used in measuring parameters on ice. We have a storage facility where we have over 7,000 meters of core stored at minus 30 degrees C. It's the only tropical collection on Earth. It's here at Ohio State. And we design and build our own drills for these projects because they have to be lightweight, portable, to get them up to these high elevations. So over the years, we have drilled all these dots you see on this global map, the places where our group here have worked. And in Peru, we've drilled 4 different sites. If you look at the Earth, the tropics, it turns out, are very important in that if you look at sea surface temperatures, you can see this in the center panel here, and you can see rainfall is very much tied to those temperatures. But when you get up to about the 500 millibar level, where all of our glaciers in the tropics exist, temperatures are very uniform. And consequently, they're all behaving in a very similar fashion in today's world. Calcaya ice cap is the largest tropical ice cap on Earth, and it's located in the southern part of Peru. And we also drilled Corapuna, which is also in south central Peru. This is what the Calcaya ice cap looks like. As I say, it's the largest tropical ice cap on Earth, and it has a fantastic record. In fact, I consider this the Rosetta Stone of tropical glaciers. So I'm going to spend a little bit of time talking about that history. First of all, you can actually see the annual layers on the margins of the ice field. We have a tremendous amount of precipitation, 3 to 5 meters a year, and there's a very distinct wet and dry season. So you can see how you drill through this and get the history from the past. If you look down at the mass, you can actually see the annual dust layers here. And if you go down into the crevasse, you can see how horizontal they are. So by measuring the thickness of those layers, you can determine how accumulation has varied through time. And this gives you an example of what actually is measured in the ice core. We have annual dust layers. Every dry season, there's a dust layer. And then annual variations in isotopes, which are a proxy for temperature. And if you measure the distance between these layers, you can determine how precipitation has changed through time. And so this is 1805 up to 1825. And if you go deeper, you can still see these annual layers. This is 1520 to 1560. Well, the Spanish arrived in this part of the world back in 1531. So before 1531, there's no written records that we can interpret. But there were huge civilizations in this part of the world. So then you can go back, this is 1240 up to 1330, and you can see how time is getting compressed. There are many more layers in a meter of ice. So that's how the history is put on the core. So here we have 3 isotope profiles. These are for the last 1,000 years. These are decadal averages. You see the little ice age in here, and you see the warming in the 20th century at the top. This record was developed 20 years ago, before we had the technology to keep cores frozen. We had about 6,000 samples, water samples, and then we went back 20 years later and re-drilled the ice field. And you see the reproducibility in the record. We were able to bring back frozen ice core, and we have an archive of that down in the freezers here at Ohio State. You can also look at how the precipitation, the net balance has changed. The browns are dry, the blues are wet areas. And if you look at the last 100 years, precipitation has actually been above average. And so when I talk about the glaciers retreating, we know it's not driven by precipitation. There are a lot of things we can do with these high resolution records. We can look at the interaction between INSO and recent warming. So if you look at these records of temperature measurements out here in the Pacific, you can see the red is the actual temperatures of the 5-year running mean, and the blues are the isotopes from the Calcutta ice cap. The other thing that makes the tropics very unusual is the precipitation pattern. The highest precipitation on Earth comes underneath the intertropical convergence zone, which if you look at a satellite photo of the Earth, you can often see this. This is where you have air converging from the southern hemisphere and from the northern hemisphere. So it's the bottom of what we call the Hadley cell. And this moves north and south every season, but it also moves as climate changes on the Earth. And where it's located tells us a lot about where the water is in the tropics. With these long-term high-resolution records, we can start to understand how this system has varied through time. So this is 700 up to 2000, and this is a Marine Corps record from the Cariaco Basin, which is just north of South America. And here, when you see decreasing titanium, it means it's getting drier. This is the Calcutta record, 14 degrees south. And then this is a record from a lake down in Argentina at 52 degrees south. And you can see this dry period here migrating as you go through time. So this suggests that the mean position of the intertropical convergence zone has moved south and to the north. The history of cultures are fascinating. This is Machu Picchu, which is from the Inca Empire, which was the largest empire developed in this part of the world. And we have the ability to look at these high-resolution records. This is the Calcutta isotope record. This is the precipitation record. And this is an El Nino record from a lake up in Ecuador. And if you look at today's world, we have an El Nino in this part of the world. In northern Peru and Ecuador, it's very wet. It's a green color. But at the same time, down south, where this ice cap's located, it's very dry. It's like a seesaw. And in today's world, El Ninos happen on 4 to 7 year time interval. It's the biggest disruption of our climate system outside of the seasonal cycle. Well, we can look at the history of archaeological records, and you can see the coastal cultures here in red, and the highland cultures in blue, and you can see they're out of phase with each other, which suggests there have been long periods where the coast is wetter, so you'd have more El Ninos, and the highlands, of course, will be dry during those periods of time. And when it becomes wet in the highlands, and you can actually see it here in the blue collars, then we have the highland cultures developing. When it gets dry again, you go back to coastal cultures, and then wet again, we come up to your Incas. And the Incas disappeared when the Spanish arrived. If you look at where the population is today, most of it is in coastal desert areas. And since about the 1940s, people have been migrating from the highlands to the lowlands. And if you look at the history of precipitation, you would say that in the past, these people would have been moving to the highlands. That's where the water is. And consequently, we have a lot of water issues in Peru. We have 70% of the world's tropical glaciers located there. And what happens to them has a big impact on the rivers that are so important for these coastal cities. The other thing we have been able to see happening in Peru is the warming and the impact of warming on the ice. This was the 1983 core, and you can see the reproducibility with the 2003. But you get up to 1990 or 1981, we can see where melting has started. And you lose the annual record because water is moving through the upper layers of this ice field. And that's happening on Calcutta, but it's also happening up in the Cordillera Blanca, where we drilled a core in 2009, You can see how this is smoothed out in here, and that's because water is now moving down through these layers. So the records are being compromised as we speak because of warming and melting taking place. The other thing that we've been doing since we studied this ice field is measuring this outlet glacier. Henry Brecker up front here has been doing this and producing maps so that we can actually see the retreat of the glacier, the development of this lake, which starts in 1991, and currently the lake covers 84 acres. This shows the retreat, and the green here shows the acceleration that's taking place. This is what Coriolis looked like this year, this past summer. And you can see that the glacier is now out on the lake, no longer calving into the lake itself, but continues to retreat higher elevations. And we've been able to observe this retreat all the way around this ice field. This is a boulder in 1977. In the next photo, you're going to look at the end of this boulder, looking out to where the glacier is located. This is in 2006, and you see how much the ice has retreated. And this is 2011. And here again, the glacier is now retreated up out of the lake. So it continues to retreat to higher elevation. Maybe more dramatically, if you look at this photo taken in 1978, here's the boulder. See the ice field there. And then this is the same place in 2006. So 25% of this ice field has disappeared since I was a graduate student here at Ohio State. You can look at the scale of these changes from satellite, and this is work by Thompson Tucker at NASA. But here's Kokaya. This is 1988 Landsat. This is the Cordillera del Pinota. And if you look at a more recent photo taken in 2006, you can see all these lakes that have developed along the margins of these ice fields. But if you look at the difference, the yellow is where ice has been lost. And so since between 1988 and 2006, 24% of the ice area in the Cordillera del Pinota has disappeared. So these are very, very rapid changes. And then we can place this recent tropical glacier retreat into a longer time perspective. And again, I'm going to use Kokaya as an example. In 2002, we found plants. These are wetland plants that were exposed as the ice retreated. And we were able to sample that and date those plants and see when the last time these plants were exposed. And then under the ice, and since they're wetland plants, there's no woody tissue, and they have to stay buried under ice, otherwise they'll decay. And so this is what the ice field looked like back in 1977. This is all a lake now. And then in 2002, this was the backside of the lake. You see the ice wall, see a person for scale, and here's where the plant deposit occurs. And the amazing thing is how fast the ice is retreating. This was in 2002. And you see in 2002, the ice was right behind the plants. These are the plants in 2005. And you see how far back the ice is retreated. So it's occurring totally around this ice cap. These plants, turns out, they date about 5,200 years before present. So they tell us that this glacier hasn't been smaller for at least 5,200 years. Otherwise, these will decay. And other things coming out of the ice, you've probably heard of. Let's see, the Iceman. He's also 5,200 years in age. He came out of a glacier over the Alps in 1991. So anything that's in the ice is getting. Well, this year, we went down and we were able to sample in a brand new place here. This was on the far side of a lake. This land was just exposed. And in here, there are layers of plants, wetland plants that are in growth position. And we were able to collect 5 of these plant samples, and we were able to date them and then compare them with 20 plants that had been dated on the other side of the lake. So these, the average here was about 4,677. The new plants all date around 6,377 years. So you get an idea how long it took for the ice to move in the past. In this case, it was advancing. So that's 1,660 years. When we first went to Calcaya, the ice stood right here. So the retreat has been extremely rapid. The impacts of the ice loss can be seen in this area, and I'm sure Bryan and Nathan will talk more about this. But here's this lake above the camp, 2006. We were surprised in 2007 to find it had completely drained. And if you go around this bend, you can see what was left of the lake, and it's actually draining to the south into another valley. So if you look at the impact of this change in drainage, and you look at the meadows down below where this stream used to flow, you can see this is all dead alpaca marsh. This used to be, up until 2006, there was water around all of these, and it was green, and it's where the local people would graze their alpaca. So the people who live in this area are already being impacted by the changes and having to take their alpaca to different valleys to find a good place. So here are some conclusions. Tropical glaciers, which are located in the warmest and wettest regions on the Earth, are particularly sensitive to high elevation warming and variability of SSDs and precipitation. The ice core records from tropical glaciers record long-term insole variations as well as long-term intertropical convergence zone migration. There is evidence that the role of climate variability in the pre-colonial history of the Andean civilizations through this insole connection with these patterns, and the rise and fall of these coastal and highland cultures are out of phase. Same thing that we see in the short-term El Nino in today's world. The observed rapid retreat of Calcaya can be attributed mainly to rising temperatures, and that balance has been above average for the last 100 years. And finally, the loss of these tropical ice fields near populated areas is already impacting hydroelectric production, irrigation, and municipal water supplies, and destroying a unique climate archive that these ice fields have preserved for centuries.
Thank you very much, Carol. Bienvenidos a todos. It's great to be here. I don't have too much confectionery sugar on my mouth, but thanks to Si Senor, that was a wonderful feed. What I want to talk about today is to take our interest from the tops of the mountains down into the valleys. And you can see in this photo here that looming over this glacial lake here called Yangaruco are the receding glaciers of the Cordillera Blanca. This is Wandoy Massif, and it sort of defines the perspective that we have as geographers taking on an interdisciplinary study of what's happening to this hydrologic system. So as these glaciers are melting, what difference does it make to people? And it also kind of characterizes my scientific career working in the shadow of these giants above me. So really what we see as part of this climate, water, and carbon program is to integrate our understanding of climate change through multiple scales of time through an interdisciplinary approach. I also would like to thank the Center for Latin American Studies for their participation in this, and acknowledge a whole bunch of other folks that are involved in this project and a lot of different funding agencies. Our group is what we call the Glacial Environmental Change, and we have a website up here. You can follow it, and it kind of is a way to encapsulate this study of glaciers and environments through many time scales and spatial scales. But I would also just add that although this is a great tribute to our educational outreach and to Carol Landis in particular, education outreach goes both ways. And when I got into this 12 years ago, more or less, I spent a year in Peru on a Fulbright and learned about glaciers and their impact to humans through this man here, Alcides Ames. And he grew up speaking Quechua on the far side of the Cordillera Blanca, on the eastern side, would take horses across the range to go to school, learned, of course, Spanish in the process, but also learned how to be a surveyor. And in the process became instrumental in measuring the glaciers and became a really important data set for us as we understood what tropical glaciers are about. So this is a real tribute to understanding science from a Peruvian perspective over time. These are just some of the students in my group, and I would give a shout out to them, just a couple of them. I don't know if anyone's listening out there on the internet, but this is Jeff Lafreniere, who's currently in Ecuador, on a Fulbright himself. Ollie's in the room, beginning to do some research in the Cordillera Blanca. This is Kyung-In Ha. She's in Michigan now, but she's been working on this project. Alfonso Fernandez is from Chile, and he's in the room with his family, working interest areas broadly through the Andes. And the next to speak will be Nathan Stansell. And here I have him pointed to both Venezuela and Peru. He can tell you more. Nate Patrick is here as well, working in the western US, in the Cordillera, of course, extending through all the Americas. We have Alicia Campbell working in Alaska, and Alex Eddy also in Peru. So what I want to do is kind of put the glacier change in Peru in kind of a global and tropical perspective, but then move on to understand kind of what we've been doing to understand just how much glaciers have receded and what their impact is to water. But really to focus then on how we framed this as a human vulnerability study, to understand glacial recession, climate change, and impacts to water resources through a coupled systems, human and natural systems approach. If we're going to look at glaciers in the world, as Ellen pointed out, most of the Earth's glaciers are in the polar regions. The vast majority of fresh water on the planet is frozen in ice there. But if we look at where mountain glaciers are, you see that we have a small but very significant part of that component distributed throughout latitudes where people, of course, also exist. So if we look at kind of the distribution of mountain glaciers by area, you can see South American glaciers are small, but actually not that small relative to other parts of the world, much bigger than Central Europe, Scandinavia, New Zealand, Africa. If we added up all the glaciers in the mountain regions outside the polar regions, we could cover 3 Ohios, just to give you some idea of scale. And of course, thinking about where people live on the planet, most of them are at these lower latitudes, which is another incentive that we have to study tropical glaciers. And if we put them into a mass balance change over time, we can think about how these glaciers have receded, but really thinned, because that's the important properties, the total volume change in the glaciers. And we see that most glaciers have been receding and thinning, but there's some interesting patterns that you get in this photo here of how these glaciers are responding. They're not all responding the same way at the same time. There's an overall thinning, okay? But there's interesting areas, including in the Himalayas, you notice, where there's some thickening. There's some thickening in the Scandinavian region initially, and then of course it's starting to thin all the more now, more currently. And these are all very consistent with what we understand is driving this in a global climate change through a loading of the atmosphere of greenhouse gases. And you can get a sense, again, of this variability if we plotted the average glacier thickness change through time, going back to about the 1960s to the 2000 here. And you can see all this kind of noise. Okay, glaciers respond from time to time to interannual balances of accumulation of snow and then melt. But if you total that, you can see this persistent and increasingly negative curve of total thinning. So we're going to zoom in now to the tropical glaciers, and Lonnie set us up nicely. The tropical glaciers, of course, most of them in Peru, but also some in Bolivia and Ecuador and Colombia, Venezuela. The Cordillera Blanca would be right between about 8 and 10 degrees south latitude, right around here. You can sort of see just there the glaciarized areas. And if we look at the loss of mass, just recovering from a cold, excuse me. In the tropics here, you can get a sense for just how, on a decadal scale, okay, the total mass loss in these regions is actually superseding those that we see in maybe middle latitudes. Okay, another reason to pay attention here. If we think about global temperature trends, we can see that overall there's been this significant rise on about a 0.1 degree centigrade rate per decade. But if we zoom in, we can see that the last 20 years, only 2 time periods have really been below the long-term average. So we're seeing an increasing temperature signal over just the Andean temperature records that we have. And if we look into the future, we can be concerned because temperature changes, these are model predictions plotted on a latitudinal scale with this sort of coarse outline of what the mountains look like through the American Cordillera or mountain chain. You see by elevation now, I circled the Cordillera Blanca mountain peaks, but these are predicted temperature rises that we might see by the end of the century. And these are on the same order of magnitude that we'd expect in the high latitudes. So this is where our concern lies. If we take a sort of a view of the Cordillera Blanca to the north, you can see this most glaciarized region in the tropics, spanning about 180 kilometers. The principal city of Huaraz is here. The Rio Santa flows, draining the western side of the Cordillera Blanca, goes to the north and off to the west to drain into the Pacific Ocean. Here we are in Peru. You can see Lima just to the south. The Cordillera Blanca is just to the north, about a 7-hour bus ride. Well, probably 8 hours now because the road's getting bad. About 25% of these glaciers have receded since 1970. About 20 million people, that's an estimate, 70% of the country, are relying to some extent on the outflow from these glaciers to the coast. As Lonnie said, a large proportion of Peruvian population lives on the coast and relies on runoff from the mountains. 267,000 people live in this area that we call the Callejón de Huaylas, which is this valley defined between the glaciarized Cordillera Blanca and the non-glaciarized Cordillera Negra. So again, here's Huascarán in position. This is a map view to show you where Huaraz is. Here's the Cordillera Blanca, and just to remind us that these glaciers are coexisting with palm trees because we're in the tropics. The seasonal precipitation is the variation that we're paying attention to because temperatures don't change much. And here's a monthly average temperature to show you that they vary only within about a half degree or so, month to month. But the precipitation, 80% of it will fall in half of the year. And what's going on with these glaciers is fueling this water supply that then becomes really important for a number of different groups of people. Not only the vast majority of the people up here that are agropastoralists, relying on this for farming, but then downstream we have La Balsa defining the input to a hydroelectric power plant, 256 megawatt production power right here. That's one of just about 12 that span between that point and the coast. And then down on the coast, we have a huge amount of industrial agriculture that's growing in demand. Right now, you're probably eating asparagus that come from Peru. It's the largest producer of asparagus, and we take most of it. Tropical glaciers are really interesting in this regard because unlike their middle latitude cousins that we might know closer to home, they don't accumulate only in this winter and melt in the summer, but they're melting throughout the year, and they actually melt most at the same time that they receive most of their accumulation. So when we look at discharge from that La Balsa point draining that Callejón de Huaylas, we can see what's known as a hydrograph. For those who are not familiar with curves, I'm going to show you a few like this. This is the time, and here you're seeing an average monthly amounts of discharge, or cubic meters per second, flowing past this point. You can see that this mimics very much the precipitation signal coming in, so that we have this very dry season and a wet season. Most variation in the wet season. And so what we're interested in is understanding not only just how much water is coming, but when is that water coming from the glaciers? Because you can see that in the dry season, when you don't have the precip input, that glacier source becomes all the more important. We do this through a mix of methods. I like to call them high and low technology. We involve a lot of graduate students and undergraduate students. Here we are doing the script Ohio, OHIO. Trying to observe and measure the total volume loss from these glaciers is one of our key questions. And we do that with a number of different techniques, and I'll show you just a few. We also are interested in just how much the water is contributing to the rivers. Now, this is an important question. It's not all that obvious, okay? Because, again, this huge amount of input that comes from precipitation, but also other end members like groundwater. So we're trying to understand the differences there. And for this, we use a number of different methods, including the hydrochemical mixing of those different properties of water. And then downstream, what is the impact to people? And for this, we team up with social geographers that are better at speaking to people. And they ask them key questions, and they interview them to see just how they are perceiving these changes and how vulnerable they are at the livelihood level to these changes. So in this regard, we do a classic geographic technique of using space for time. We focused in on a number of key watersheds within this Callejón de Huaylas that have different amounts of glacier percentage coverage. This allows us to then assume that these changes through time might mimic what we see through space. Okay? So in this case, we've done about 3 years of a study so far that's ongoing, where we selected key watersheds, the Yanganuco here in blue, that has about 25% glacier coverage. And we've sampled about 52 households. That's about 2.3% of the population that's there, through a number of different strata of livelihoods. And then the Quilca-Huanca Valley, right above the principal city of Huaraz, has about 17% glaciarized coverage. And we've interviewed about 32 households, about 10% of the population. And then to the south here, we have the Querecocha Basin, which only has about 2% glacier area. Interestingly enough, when we look at the total glacier ice coverage area for the Cajon de Huaylas itself, it's less than 10%. Okay? So here, in following, again, Alcides Ames, who did the first work in actually surveying this glacier, this is the Llano Moray Glacier, just gets you some idea as to what's happening to the glaciers in the Cordillera Blanca. And it's very similar to the story that Lonnie just showed you with the Cordillera Caves. 1982 through 2004, just a dramatic recession of the front of this glacier and the subsequent formation of the lake in front of it. Here's a photo from 1998 when I first got there as a graduate student. And we'd go monthly with my friend Jesus, and we would measure the discharge coming from that lake and also survey the glacier. And if you look carefully at the front of this glacier and at this rock in the middle of the glacier, which is pretty much at the same level with the ice and the ice up here, how this changes to 2010. Okay, you can notice dramatic frontal recession, but also notice how the thickness of this glacier really changes. You can also notice some infrastructure set up to measure the discharge in a real-time sense. And then what we've done is mix our low-tech monthly measurements with a flow stick of discharge from these lakes with some more high technology of a laser sensor to get at just how much surface deflation we're seeing in the ice. And this is using a technique called LIDAR, or light distance and range. This is something we accomplished with some great angst, but we've only been able to get about 70% of our targets, and I can tell you in depth more about that offline. But we did get some great results that have been able to help us understand more precisely what's going on with glaciers. And here's that same Llano Moray Glacier draped over a high-resolution digital elevation model, showing where that 1962 position of the glacier was and where it is now in 2008, and just how much not only surface area has been lost, but the total volume, which is, again, is the key question of water resources. And we've been able to look at just the relationship then and fill in the gaps in time using satellite imagery, that over 86% of the surface area has changed, whereas the volume, we've had an average surface lowering of quite a lot, about 54 meters. Okay? So this thing is literally shrinking and disappearing from the top down. And as you do so and you expose more rocks, you get radiation feedback, and it melts even faster. So what this means for scaling relationships, which are kind of important when we try to take our empirical data and scale them up over larger areas, is that the formulas that have been used based on previous work really underestimate by about 2 to 12 times what's really happening to the volume change of these glaciers. And as we go, again, to broaden our scale of interest from that upper glacial lake to where people are living in the valley, we do a number of different techniques to look at the water coming from those glaciers. So we mix the waters from different chemical signatures, and we're able to use that as a proxy for volume and look at how much water is coming down that river. But then we're also able to look at historical records to calibrate some models to simulate what might happen as glaciers recede. And this shows you a multi-decadal look from about 1953 when they started measuring the discharge from the La Balsa, about to the end of the 20th century here. And we can see a significant decrease in the outflow from the entire basin. So when you see that, it's not obvious what's really going on, but you're compelled to think, well, wow, is that all glaciers? Or is that maybe an increase in human use? Okay, what's really going on here when we see this? This is statistically significant. And so our key concern really is to think again about the seasonality of our water supply and the overall abundance of it. And for this, we've also got to consider the fact that as glaciers melt, they're really in the short term going to give us more water. Okay? So if you can conceptualize this in some sort of a space here where you have some amount of time, you don't have to look at units because they can be arbitrary at this point. And here's the discharge in a river coming out from those glaciers. And as the glaciers start to, if the glaciers are in equilibrium, you won't see much change in the river outflow. As soon as those start to melt, however, you're going to have more water going into the river, so you can have more water available. But then afterwards, as that mass decreases all the more, you'll slowly get less water available until you reestablish an equilibrium point that's going to be lower than your initial point. Okay? So what we're interested in is trying to understand where we are in this kind of conceptual hydrograph in the region, because if indeed we've started to see this long-term decrease in supply, maybe we don't actually have a whole lot of extra water around, which is what a lot of people have been assuming. So that's really what our interest has been. And what we've done is taken again a look at how the rate loss of glaciers is impacting the hydrology. And we can see that the annual fraction of glacier loss in percentage is something around the order of 0.6% per year throughout the whole watershed. That's changed through time, of course. So the average value from 1990 to 2009 was double that from the period of 1930 to 2009. This is an acceleration. So again, as you accelerate your mass loss, you might expect to see some sort of change in the hydrograph. So in order to do that carefully, what we tend to do is re-instrument a number of positions through the watershed. Now here's a story of social geography, and also a story of economic reform in Peru. Okay, in 1950, there was a lot of economic interest in the hydropower potential for this valley. So they set up an operation to measure, and set up some nice instrumentation that was mechanically winded stage recorders in big steel pipes that lasted through the entire second half of the 20th century. But after late 1990s, Fujimori was in the office and he decided that he needed to privatize the state-run hydropower company. So they downsized, and all that instrumentation was not able to be upkept, so we lost a lot of data and we weren't able to maintain them. So what we tried to do is re-instrument those same places using maybe some more sustainable technology, hopefully. This is some pressure transducers. This is Michel Barrera, who's a Miguel grad student who designed this for us, setting up in the same location where those old stations were set up in the 1950s, which gives us some continuity to then look at rates of change. And what I'm going to try to do is show you ways that we've tried to model what the glacier retreat is doing and what that might look like through a hydrograph here. So here you see sort of a model simulation of what is going on, and you notice that, did everybody see that? Did it work? Okay, so as the glacier recedes, you notice that you see the discharge starts to increase and then decrease again, and that's the black line, okay? And then you also see that the rate of recession or variability tends to increase in the red. So if you have less glaciers, you have more variable discharge. And then this is all contingent upon the rate of recession in that green line, okay? That I just showed you, the change in glacier extent. So anyway, what we can do is then actually project into this kind of hydrographic space 4 different time zones, okay, where we might be in this hydrograph through time. Are you in the first phase where the discharge is starting to increase as the glaciers are melting? Are you at the top, cresting at the peak of the water availability? Or you are starting to decline on the sliding side of this peak? Or then maybe stage 4 where you reestablish a new equilibrium. And so what we've done by modeling each of these catchments in succession is sort of put them on this space. And really, the surprising thing is that 7 of the 9 catchment areas that we've studied have really crossed this critical transition that we're calling peak water. Okay? And they're exhibiting now a decreasing dry season discharge. And La Balsa itself, if you look at it, that's the whole Cayenne de Huaylas, passed that peak water probably in the 1970s, which is consistent with that decline through multi-decades. So how are livelihoods actually affected, and what are people perceiving of this? Well, again, I outlined just a little bit of what we've done here. I'm not going to get into depth here because this is a whole other talk, but we've been able to talk with people and get a really resounding perception of change. People are very keenly aware that these glaciers are changing. And that climate is taking place. Climate change is taking place. So it's not just that these glaciers are receding without a climate input. More than that, people are not just thinking about warmer temperatures all the time. They're actually becoming more vulnerable to what are extremes in climate. And if you were attentive, Carol just pointed out to me that an article that was released describing this phenomenon of friajes. If you're familiar with this, what this is during the dry season, people are getting hit with a lot more cold outbreaks. And so this is something that we picked up in our surveys as well. A lot of people are getting hit with strange weather patterns that actually interrupt their agricultural cycle, make them all the more vulnerable to changes in the water supply. So here's just a screenshot from that recent article, freak cold events, which are becoming a more frequent occurrence. So shifting climate extremes, shifting water availability, people are responding very strongly to these changes. Although they're saying that in the short term, there's still water available. They're not finding shortages. Okay, they are seeing changes in spring flows and other different parts where they get their water. So for more details, you can look at some of these other publications we've had out. But really what we're saying here is that households, at that household level, this is where we figured this is where the rubber hits the road. If we can interview people where they live and see how their livelihoods are impacted, this might tell us a story of perception and change. They're seeing negative changes in their lives due to these recent climate changes. I would advocate to, I'll give a little plug for a book called In the Shadow of Melting Glaciers, written by Mark Carey, who's now collaborating with us. He's a historian, okay, and he's gone through the archives and looked at just how melting glaciers in this region have really impacted livelihoods, not only in in terms of water, but through hazards. As these glaciers get steeper and further back, they're more precipitous. It can fall, especially in the tectonically active areas. So ice avalanches and runout floods have really shaped the psyche of this region. And so what we're seeing as we go downstream is that with this diminished supply, there's an accompanying change in demand. Okay? You can't really get this full story without looking at the social side of things. So for this, we have to look not only at the glacier situation in the water, but at the communities and water supply. And we can see things like urban water use growing. In Huaraz, the principal city, we've seen they grow from about 3.2 million to 4.8 million cubic meters in 2010. In Caraz, one of the other regional centers, that number goes from 502,000 in 1999 to 896,000, so almost a doubling, okay, in that time interval. This is just relatively recent time. Trujillo, which is a major coastal city, big cultural center in Peru, had zero of its water coming from the Rio Santa in the 1980s. Well, due to a big engineering project, they now have 70% of their potable water coming from a different watershed, which is ultimately coming from the Rio Santa. Hydroelectric demand has grown. You can see just some of the numbers here of the Caño Papato, which is the power plant defined by La Balsa in Cajon de Huaylas, and the capacity growing. This has been caught up in terms of how much the water is actually worth when you look at money. 80% of electricity generation in Peru is from hydropower. So if we run scenarios, this was done by the World Bank, you can come up with some cost estimates of what the future might look like without glaciers. And then down to the coast, you really see dramatic increases in agricultural production. When you look at irrigation hectares, so in 1958, 7,500 hectares were irrigated. Now, in 2004, through the Chavimochic project, 144,000 hectares are being irrigated. And another 30,000 through another project called Chinecas. So what this sets up is this hydrologic interdependence across this escarpment, where again, a large coastal population relying on runoff from the mountains. Only 2% of all the water resources in the country are available for that coastal region. Okay, most of it's over here in the Amazon basin. So what does this mean? Well, it might mean we'll see tunnels through the Andes at some point. Okay, so water is primarily available in rivers that are fed by the glaciers. The Rio Santa is the second largest flowing river to the coast, but the most regularly flowing because of that buffer. And here's the asparagus story. This is what a coastal desert looks like when it's green. Wonderful for growing asparagus. Okay. Here's just showing some of the production changes through time. And the Chinecas the Chavimochic is an abbreviation for a number of different valleys that is getting water now from the Rio Santa. So we're moving water outside of the natural watershed, and we're now into stage 4 of a major production which really had plans that went way back to the 1920s. So again, water plans were made with this assumption of a lot of water that was coming at that time because of this melting mass of ice. And so we're seeing some interesting financial interests internationally here. And just to summarize briefly, glacier surface area is really dramatically decreased, as I showed you. But not only that, the volume surpassing what we've estimated. And then when we run our models, we can sort of see that the glacier-fed discharge has passed its peak moment in time, setting up some interesting changes down the road. What does this mean? Well, it doesn't mean a huge, all of a sudden, no water scenario. What it means, however, is a difference of about 30% of the dry season, which is a big number when you start to look at the growing demand and the competing interests. And so really, this increasing impacts to resource-dependent household livelihoods follow a number of these multiple vectors of vulnerability, as we're calling them. But then we really get into this political economies of contention, and I'm just going to read this because this is not my work. But the glacial recession and climate change have either created or influenced widespread environmental and social change in the region, is the way that my social colleagues, both the historians and social geographers, are summarizing this. The political economies of these tensions are not future concerns, they're already underway. We've had a graduate student finish up a year down there looking at how the watershed management on multiple levels, from local governments on, is really intensifying conflict scenarios. So I'll leave it at that, give you a list of publications here, and make way for Dave.
Most important thing is figuring out the pointer. So I put this together mostly to try to follow up on what both Bryan and Lonnie were talking about. In some ways, my work complements and fills in the gaps of a lot of the work that Lonnie does. My work may not be as sexy at first glance as Lonnie's ice core work, but Ice cores are limited to only a few regions of the planet where we can core them and have access to them, but lakes are found almost everywhere. So even in regions where the glaciers don't exist today, they did in the past, and the glaciers are still there. So it's early in my career, as Lonnie points out, those glaciers will be gone soon. So I need to have something that I can study long term, several decades. So it's laughable, but it's true. So my work, mostly studying on the lake sediment side of things, motivation is to try to look at the longer term perspective of things. To place things into a longer context of work that Lonnie presented. We see this drastic retreat of glaciers very recently. Well, how important is that in the long-term perspective of things? How crazy is that? How abnormal is it really on longer and longer time scales, namely thousands of years or tens of thousands of years? So I'm trying to use the past to better understand the current trend of glacial retreat, to again try to just put that into a bigger context of what's really crazy versus what's sort of, quote, natural. And with all this information, hopefully we can compile it and use it to predict and to better plan for future changes, a lot of things that Bryan pointed out in terms of water resources. So this picture here, this nice landscape shot from the central region of Peru, is sort of taken in the backdrop about a 3-day hike after Lonnie's intro slide of the Cordillera Blanca with Huascarán. So this mountain peak here is sort of back in the backdrop, sort of adjacent to where Huascarán is, and we recorded this site back in 2009, but it really captures my research interest of combining glaciers and lake sediments as recorders of climate change. So just a little bit more background, just a term for you, the Holocene. I'm interested in the Holocene timescale changes. The Holocene is a fancy word for everything over the last 12,000 years. It captures the time of when the last major ice age ended and we entered into a period of, quote, stable climate. Now I use the term stable very loosely, because as we know from a lot of the records we produced the last few years, is that that Holocene, that last 12,000 years, has actually been punctuated by a whole bunch of different sort of climate change events that are worth further study. Over this sort of 10 to 12,000 year time span is also a period that affected humans, especially in South America. In a former life, I wanted to be an archaeologist, and that's part of why I first went to South America, because I wanted to understand that human link to environmental changes. And since then, I focused more on sort of the geological aspect of it, but I still keep coming back. Ultimately, what's important to me in terms of how do these changes in temperature, changes in precip, changes in water resources affect people. So again, so the glaciers provide evidence of these past environmental changes that we can better use to understand. Just one example, things like the cultural record, major shifts in population, things that Lonnie already talked about. So my focus, Lonnie focuses on the isotopes and other aspects of the glaciers. I like to study the dirt or the sediments they leave behind. So sediments in down valley lakes, this picture is really washed out, but there's a little lake here. This is from some field work we did in 2009 with Bryan, my first field season here at Ohio State. But these lakes that sit down in these valleys serve as little sediment traps. So what the glacier's doing at the valley, churning up the bedrock and spewing out those sediments accumulate down here. So long after those glaciers have come and gone, the sediments that were created from their processes are left into these little sediment traps that we can then go core. So in addition to the lake sediments, other landforms in the region, we can study them, we can sample them, we can look at them, and together, by combining those different lines of evidence, we can put a more detailed perspective of the past changes in each respective watershed. Here's just a couple of pictures of the types of things we go map in the field. Present-day glacier up here. You can see major changes in vegetation marked by these sort of ridge lines that stick out. These are called moraines. That's just a fancy word for sediments left on the sides of glaciers or in the front of them. And so we can go map these moraines. Here's another nice one here. This nice little knife-like edge running along here. That was deposited as that glacier came down that valley and pushed sediments and left them on the side. So there's very clear evidence of where those glaciers were in the past, so we can go map them in the field pretty easily. These lakes were formed by glacial processes, so it's very clear evidence of where that glacier was at certain times in the past. We can then go sample those boulders and apply a series of radiometric dating techniques to figure out when those boulders were placed there. We can also go into the lab, and this was that same LiDAR image that Bryan was talking about earlier. This is just the adjacent valley. This thing has a 1 meter resolution, or close to that, in terms of the elevation data that's produced by it. And this picture doesn't do it justice, but it really shows this really striking detail that we can map out the current extent of the glaciers today, and we can find all these little knife-like ridges going down valley. They're very clear. So we have remotely sensed data that we can use to map out glaciers in great detail, and we have that field-based sense where we can go and walk and map out those things that we can get or see on foot. This can be done in a day. This valley took us a 4-day hike up here, which we had to leave early from because the cows ate all of our food. So, true story. But just the logistics of it, the effort it takes to get up here to map something out that we can just see in a satellite image like this, or a DEM produced from LiDAR. So we can take those field and lab-based observations, come into the lab, do some computer modeling, and we can apply a very fancy set of equations based on what we know about glaciers that cause them to change. We can run various model simulations where we can virtually grow these fake glaciers. And what we do, based on those algorithms or whatever we plug into the model, we can run them out until we get glacial ice that grows virtually to match that mapped extent of where we know the glaciers were in the past. And so what I gave you here was 3 different sort of screenshots of different moraines, those sediments left by glaciers from the past of known ages. We ran our computer simulations out with changing things like the amount of precipitation and a relative cooling. So by changing temperature and precip, turning the knobs, if you will, to grow a glacier, we can hit those targets, which are those map moraines that we see in the field and those satellite images. And just so 500 years ago, we came up with a value of 1C, just to give you an idea. 16,000 years ago, 2.75, and 25,000 years ago, about -6. But these types of models we're constantly refining based on what we know about glaciers and what we have from sort of independent paleoclimate data. So those sediments I told you about, or those boulders that are left behind by glaciers, we can go out there. It's not that sophisticated. With a hammer and a chisel, and we can break a piece off the top of those things. These rocks sit out there and they get charged. They get bombarded with charged particles from outer space. It sounds like sci-fi, but it's true. We call it cosmogenic rays. It's just charged particles coming from the cosmos. And those charged particles interact with those rock surfaces and it changes the chemistry of them. And so we can go look at isotopes of certain elements like beryllium, aluminum, and chlorine, and we can look at basically the more we have of these, the longer that rock's been sitting there getting bombarded by those charged particles. And we know through basic physics and basic chemistry how long it takes to accumulate that much stuff. And so we can come up with a timeline of events. We can figure out how long this boulder's been sitting here exposed there on the landscape. Knowing that it came from a glacier, those ages are going to tell us when that glacier dumped that rock there. So these techniques give us little snapshots of when the glacier was there and then when it retreated. And it tells us where that ice position was in the past. But it really only gives us snapshots of things. We call them minimum ages. What's going on with the lights? That's okay. When we combine it with these lake sediment records, those boulders give us little snapshots, but the lakes give us a continuous record. So this is actually a lake from Venezuela, but this little fine layering that you can see in this core, roughly each little layer represents about 1 year to 2 years of time. So we can go back and we can get really detailed evidence. The lighter colored stuff, sediments that came from a glacier. The darker colored stuff is just organic stuff, brown lake mud, you've all seen that. So we can see the 2 end members of glacial sediments versus not glacial sediments. Where this light colored sediment is there, the glacier was there. Where it's dark, the glacier was gone. So combined with those boulders on the landscape, we've paired up with these lake sediment records to get a really detailed timeline. So not only do the lake sediments tell us about the glacial sediments, it gives us other information what's going on the landscape. It collects pollen. It tells us about the vegetation. The organisms that live in the lake are sensitive to climate. So we can look at those different types of organisms, and again, just independent lines of evidence to figure out what was going on the landscape when that glacier was advancing and retreating. How we get those records, it's not that sophisticated, not as sophisticated as Lonnie's, but it's the same basic principle. We have to backpack a bunch of stuff up in the mountain. And these are just plastic tubes that we glue together. And then we put them on a boat. And these boats have to be backpacked up the mountain as well. And so these are just cheap little several $100 boats, but they do the trick. And we fabricate some stuff in the lab to build some sort of apparatus or torture device, however you want to call it. But it's a torture device and we have to pack it up the mountain. But we strap it to the boat, we go out in the middle of the lake, and we pull out tubes of mud. And like Lonnie does with the ice cores, we bring that mud down the mountain to analyze back in the lab. So what's nice about lake sediments is those dark brown layers are full of organic matter, and we can radiocarbonate that. So here's just an example of a profile of radiocarbon ages that I have on a lake sediment record, so that those radiocarbon ages give us the chronology, so we know when exactly those advances and retreats took place. And those lake sediments give us bracketing ages of glacial events. So again, we go with the assumption that those light-colored, mineralogenic, mineral-rich sediments come from the glaciers. And so when those sediments that are trapped normally in glacial ice get dumped into lakes, that's what we use to reconstruct those really nice timelines. So just to give you a few examples here, this is from Laguna Geschke in Cordillera Blanca. Bryan and I had the joy of coring this thing in 2009, and we've been working on it since. One of the best records I've ever pulled out. I don't want to blow you away with all the data. These are just a bunch of different things that we measured that all tell us the same thing. The more of it, the more glacial sediments that we have. So going from 12,000 years ago to the present, what we see overall is there's sort of a trend of advancing glaciers in that watershed. Again, more of those types of sediments, advancing glaciers. There are some notable exceptions that I'll come back to here in a second, but overall, the last 12,000 years, glaciers were progressively advancing in this particular valley. Okay. So progressive glacial advance during the Holocene. Okay. So again, to summarize, those last 12,000 years characterized by overall advance in glaciers. And when we combine it with other sediment records, namely ones, the lake sediment, Lonnie talked about Calcaya. Here it is back in the backdrop here, but here's another lake sitting right here, and its sediments tell us that right at 5,000 years ago, we see a huge change in the amount of those glacial sediments getting deposited in there. So Lonnie talked about those plants that were being exposed. They date to right around 5,000 years ago. Well, this lake, like a light switch, turns on at 5,000 years ago. Boom, and it starts recording glaciers, glaciation of about 5,000 years BP in that watershed. So I noted or mentioned that there's some notable exceptions, and one of them in this Geschke record is this departure right here from between about 1,300 and 550 years ago. So that to me says that there was a glacial retreat during that time in this particular watershed. Why is that? It was probably a period of drier conditions. It's something we're still working on, but it really stands out as being abnormal compared to the rest of the record in this longer trend. So there it is again. And so there's also what's notable is the very recent, which it's sort of cut off on this scale, but very recently you see departure in these types of sediments as well. So what's unique on these longer time scales for this particular record is this window I've highlighted in red and the very recent stuff. Okay, so we know that some of these major shifts coincide with the archaeological record, which I won't go into because I don't have time. But what's notable is just how unique it is that this period of departure took place in terms of the glacial retreat. Now, the periods of glacial advance, to me, in this part of Peru are the norm. These periods of glacial retreat on this 10,000-year time scale are the exception. Okay, but that's sort of a potentially reckless statement to say that over the last 10,000 years it's normal for glaciers to be progressively advancing in the tropical Andes, because that implies that this most recent stuff is really shocking into that sort of context. But I should also point out that this is a record that we have in Peru, and if we go up to somewhere like Venezuela, it's the exact opposite trend that we see. So jumping across the equator, going from 8 degrees south up to 8 degrees north using these exact same methods. This is a site I have called Anteojos in Venezuela. Here's my age model here, radiocarbon ages. The trend through the Holocene is the opposite. So instead of this gradual increase in glaciation, we see a gradual retreat of glaciation. And Lonnie picks on me all the time about, well, that's just one record, but over the last few months we've come up with a bunch of other ones. Here's Mukubahi. Here's our boat for scale, just to give you an idea. Here's some of those moraines again, those sediments left behind by glaciers. Lake Mukubahi, same thing overall, but it is recording the Little Ice Age of the last 500 years. We're seeing an increase in those glacial sediments again as well. But yet another site that's showing glaciers retreating over the last sort of 10,000 years, mirror image of what Peru is doing, with the exception of the recent stuff. Okay, so that's two. You're still not convinced. Well, here's Pico El Toro, the bull. This picture looks awful. It's awful for a reason, because it was taken in 1910. And this right here is a little glacierized peak, and that's Pico El Toro back in 1910 from Venezuela. This is what it looks like as of almost exactly 1 year ago today when we recorded this thing. This was 6 days of backpacking to get to this site. There's absolutely no glaciers there at all, or really no evidence of ice being in the catchments at all today. But we know there was historically, because we can see it right there in these crude pictures, but it's there. There were glaciers there in the recent past, so that we know during the Holocene that this thing was sensitive to glaciers being there and glaciers retreating. Here are the data for, I use titanium here. Titanium, again, is just one way of measuring those glacial sediments. The more titanium, more glacial sediments, more glacial activity in that valley. So same type of thing. Early Holocene, we see glaciers were there. Overall, during the Holocene, that ice was mostly retreating, except for sort of in the recent past, in the Little Ice Age, we see those glaciers advancing again. Okay? So again, the take home is that Peru, certain valleys look like ice is sort of progressively advancing over the last 10,000 years. Venezuela has the opposite sign. Both tropical, but they're both on opposite sides of the equator. And so trying to understand why those systems are a mirror image of each other, or why those glaciers are behaving differently, you have to get into what actually causes glaciers to vary, what causes their glacier mass balance to fluctuate through time. Glaciers are sensitive to both temperature and precipitation, and you always have to remember that you're looking at an integrated signal of both of those parameters when you're looking at any glacial record. And so trying to understand how much temperature, how much precip, how much those relative influences play on a glacier is sort of the state of the art of what we're trying to do in these types of studies. I stole this from an old talk Lonnie had online of just precip at latitude, and even though they're on opposite sides of the equator, similar degrees north, similar degrees south, precip in Venezuela is quite a bit higher. It's really, really wet in Venezuela, and if you work there, it's miserable, Even in the dry season, it pours rain on you all the time. Peru has a very sharp transition between a dry season and a wet season, and it's relatively rare to have rain on you during the dry season. Venezuela dry season doesn't really exist. It still rains on you. Okay? So what that means is that glaciers are sensitive to whatever they're limited by. If it's a really dry region, they're going to be precip-limited glaciers, and they're going to be more sensitive to the amount of precipitation that they get. If it's a region like Venezuela where it's already really wet, those glaciers aren't going to be sensitive to a little bit wetter, a little drier conditions. They're going to be a lot more sensitive to that temperature change that's going to take place. So Peru is going to be a mixed signal of both temperature and precipitation. And I think that what we're seeing over the Holocene is that added feature of precip driving those changes versus temperatures, which we're mostly recording in Venezuela. But nevertheless, they're both sensitive to temperature and precip. Venezuelan glaciers are a little bit more sensitive to temperature changes, which explains that overall Holocene pattern. But when you look at both records in the recent past, i.e. the last 1,000 years, Venezuela and Peru are behaving very similarly. And I think that over the last 1,000 years, that temperature component is now integrating those, or explaining both of those records that we see. So at different times in the past, precip plays a bigger role in Peru than it does maybe today. So there's a lot of future work to do this project. I've given you one record of a multi-year project that Bryan, Mark, and Don Robel and I have funded through NSF to work on these types of things. And we're trying to go, I showed you one slope from Peru. And if we go to a bunch of different valleys that have relative sensitivities to that precip, maybe we can nail this down a little bit more in terms of the actual overall contribution that precip has. But we have a lot of work to do, and we have field seasons planned for this summer and next year as well to get more of these records from areas that are really wet in the Peruvian Andes and areas that are really dry to try to nail this down a little bit further. So we have a bunch of students that are also funded to go on this. We have a grant from the Keck Undergraduate Consortium that gave us some generous funds to take undergrads with us year after year to go work on these projects as well. So we're supervising numerous undergraduate theses projects on these types of things, where some students are looking at cosmogenic ages of boulders, like from this moraine here. This is a valley called Yanacocha in Peru, and other people that are working on the lake sediments. So with that, that's all I have. So thank you very much.
Any questions for the panelists?
I would like to ask you, you said that yes, that there is a lot to be done. Do you have any international group where you all participate and working together, since this is a global issue, or?
I think I can speak on behalf of all of us that every project we have has multiple nationalities involved in every aspect of it. I couldn't do a lot of my work in either Venezuela or Peru without local scientists there that help us, you know, with every aspect of it. And so, yeah, I didn't even go into it. I have a lot of colleagues in Spain and other universities that are looking at different aspects of the pollen records in cores, and biologists that work on different aspects of the samples that we take. And so, yeah, it's a part of a huge international collaboration. If it's not in the field, it's meetings where we're generating ideas with other scientists from all over Latin America, all over Europe, etc. So, yeah, and when you say there's a lot to do, the more records that we get, and I'm sure these guys would agree with me, the more records we get, the more confusing it becomes. You know? If you had a record from Peru, it would be a lot easier than if you had 15, because they don't necessarily always agree. So,
There's an interesting large project starting in Peru to get a long core at the lake called Junin. I don't know if you know Laguna or Lago Junin. It's a very big lake. It's got a lot of sediments in it, and it's beyond the reach of where the glaciers got to. So it's got continuous records potentially through multiple glacial cycles. And that was kicked off last summer, right? We had a workshop in Tarma, and that brings Peruvians as well as international scientists.
there were probably about 30 scientists from all over the world that were, it was a brainstorming event to collaborate on various proposals to drill Lake Junin, which the lakes I showed you are 10, 15,000 years old, but Lake Junin is hundreds of thousands of years old. And it's, you can't just backpack equipment in, that's a drilling project. You need millions of dollars to go in and drill those types of things. And that type of project especially needs a huge international collaboration to pull that thing off, you know. So, but it's the information that we could extract from a lake system like that, and not just climate, you know, the tectonics and the earthquake history and all these other things that can come out of these types of sediment archives are really impressive. So.
I would say that we also, we've been working in Peru for 35 years, and so a lot of the people there started when they were young, and they've stayed with us all through this time. Some work for a power company, our mountaineers, our guides are Peruvian, and we'll take them to China with us when we go to the Himalayas. And so our teams are very international.
So on a massive scale right now, we're seeing, like, in Western society, we don't really directly experience all these changes. Do you think there'll be a point in time within our lifetimes when it'll be unavoidable to just say it's not happening, as opposed to, like, we're actually genuinely experiencing big changes where we're at? Yeah, like, for example, you know, this past January is a good one. This has been very interesting. But Louis, when do you think the point will come in time where you can kind of objectively make these arguments and things like that, as opposed to people that want to run around and say no?
Well, it's for sure, if you live in a place where there's glaciers and you can see the change, then you're convinced. If you give a lecture on global warming in Alaska, it'll be standing room only because they watch it. And if you go to Peru, or you go to Kilimanjaro in Africa, these people have watched these glaciers retreat over the last 100 years. But there's a real issue here is that young people like yourself, you have a perspective of what the weather is like, but it's a shorter term perspective. As you live longer, you can see these changes. And certainly when I came to Columbus in the 70s, we had blizzards that shut down the state for 4 or 5 days. And you don't see those things anymore. But you probably don't.
Any other questions? Yes.
Hi, can you make any predictions about the socio-economic, I guess, dangers we're in from the glaciers retreating? Like, what kind of things would start affecting the Peruvian, maybe the rest of the global economy? Like, are you able to make any predictions based on that?
Well, I think certainly if you look at Peru, where 76% of their power is hydroelectricity, that the water becomes a huge issue, and especially water during the dry season, because you have to have power year-round. And already they're investing in coal-burning power plants, oil-burning power plants to make up for lack of power on the grid. And so these economic forces are huge. And they're occurring in Peru, but they're occurring around the world. You go to China, you see similar things happening.
Does Peru contribute much hydrologic power to other countries? Or
They consume most of it internally.
Into-
Yeah. But it's an unusual country because it's, I think several of the speakers pointed out, there's so many people living in the coastal desert, these huge cities, depending on one river coming in, and then you have the power, depending on those same rivers, and then you have agriculture like the asparagus, depending on that same water. And you have to ask whether this is sustainable in the long term.
Interesting, I mean, Peru's been going through boomtown, and 9% growth economically per year for a while. It's largely mineral export, and this large-scale export agriculture contributes to that. I mean, you can make an interesting case for virtual water export in the form of asparagus and other fruits, alcachofas as well. I mean, there's other things that are being exported, grown in the same area, sugarcane and stuff. So when you think about the economic impact of changing thresholds of water and who gets the power and can make those decisions, I think it becomes an interesting multi-corporate kind of story. Mining interests, by the way, have really grown as well. When we mapped, Alex made a nice map for a recent conference that had a backdrop of all the recent mining claims that are being made through that Rio Santo watershed, and it's huge proportion of the watershed. Not all active, but they will be. And so, you start to then incrementally change those demand structures. Interestingly enough, in the latest census that came through in 2010 for Peru, Lima was no longer the most rapidly urbanizing area. It was the intramontane cities like Huaraz and like Huancayo, another of the old breadbaskets of the Incan Empire, which is in between mountains, very much closer to the glaciers, that were growing faster. So these centers are, interestingly, like the highland cultures, is sort of taking advantage of that water that will change. And so it's these increments, and then of course how you treat the water or don't. One of the things we did last summer was do a reach study. So we started at the Pacific coast, and we went along the Rio Santo all the way up to the glaciers. And we sampled discharge, and we sampled for chemicals, and we sampled for trace metals. And basically we could see dramatically how 80% of the water is derailed before it gets to the ocean through these irrigation schemes. But the yield of metals coming into the Pacific is tremendous. There's just a lot of suspended metals in that water. So clearly there's some contamination issues. As you have less water, the quality of that water becomes all the more important. Basically, the habit in Peru is you throw everything in the river because in the rainy season it goes to the coast. So water treatment and water quality are going to be all the more important.
One of you made a statement about the possibility of building a tunnel, and I'm assuming, I remember reading an article not too long ago about possibility of a road being built. trade transportation. But I'm assuming what you're talking about has to do with water delivery. Could one of you speak to that?
I made that comment, and basically, if you think about where that water supply is, you get a huge amount of rain that comes through the Amazon basin. We're still in the zone of the easterly, so all that precipitation that falls in the form of snow and ice is falling, originally coming from the Atlantic, transported and recycled across the Amazon basin. So if you can then extend your catchment across the watershed divide, you would have more water source. That's what I meant by tunnels. Now, I think there's been talk about tunnel projects.
There is one on the books for Lima, where they would go and capture water that now goes into the Amazon and bring it over to Lima. But of course, this creates all kind of issues for the people who depend on that water on the other side of the mountain range. And a lot of times when we think about solutions, one of the things you can do for a loss of glaciers is build dams, because the dams can be used to collect water during the wet season, let it out in the dry season. But when you actually look at implementing this, there's a classic case with the Socio-economic River, comes from the Kokaya ice cap. They wanted to put in a dam because the water ultimately feeds the Machu Picchu power plant. But in order to do this, they had to flood these huge areas where local people live. So there was an uprising. They burnt the house of the mayor in Lonnie, and eventually the government pulled out. We're going to do this. So a lot of what you think would be logical solutions become very complicated when you're dealing with people in these areas.
In Peru, who controls the water? Is it privatized or is it run by the government?
Legally, there's a primary right to everybody to have water, drinking water. That's a guaranteed sort of human right that's maintained. In 2009, they revamped the water law. But what's interesting is that the wording is subtly changed so that agriculture is also an important listed use of that water. Okay, meant to be for human consumption, of course, but when you think about the reality of who does the agricultural production in Peru, you realize that it's these large coastal projects that are a combination of private and government funds, then that equation changes. I don't know much more than that. This is an active area of interest for us to consider, is to think about water rights. What happened is, in the wake of that 2009 water law change, was that all of the watersheds were meant to reorganize and have corporate decision-making about how to allocate water. And instantly, there was an organization formed in Peru to actually quantify how much water you should have. And so people are signing up, and there's a lot of people, saying what their rightful amount is. Now that's good and bad, right? Because all of a sudden that becomes your limit. If that's your agropastoralist, your incentive might be to say you need more or whatnot. But you're also meant to organize all the local people within the watershed to discuss this. And these water organizations are not really playing out as imagined, ideally. But they are going on right now, and so we have people looking at that, how both the laws are changing and how people are perceiving those laws. As Lonnie alluded to, there is conflict emerging. Another example in the Cordillera Blanca region, a whole water, one of the largest lake in the Cordillera Blanca is Laguna Paron. And it's dammed, it's controlled, and it's a good control buffer for the hydropower plant. And it was maintained by the private company. Okay, it's a North American conglomerate, Duke Energy, anyone heard of that? And so they, but nevertheless, the people that were there didn't like the fact that they couldn't control the outflow to that lake, because they'd see all the water going at night and they didn't need it for agricultural production to get upset. They also didn't like the fact that they saw the lake levels dropping dramatically. So they actually occupied the valley. Okay, it's very much like an occupy movement. It wasn't, thankfully, any violence, but they blocked the road. And instantly the folks left from the company. They didn't want anything to do with it, any conflict. And so this is still being negotiated as to how this gets resolved, because it's almost a precedent-setting case of locals sort of getting upset, taking ownership of their resource. Anyway, yeah, did you have something?
Yeah, so one gets then to the conclusion that big money is what rules what we eat, what we consume, what we, they have the power to make the decisions, right?
That would be a hard to avoid that conclusion.
Why?
Well, there's certainly a lot of local protests. I know that maybe 3 years ago we had a group down to go on a building project. But we had 3 pickup trucks. And in the back of one of the trucks, we had shovels and things like that. And that truck was identified as being associated with a mining company. And so it was pelted with rocks and windows broken out from the local people who they do not appreciate what the mining companies are doing, and their lifestyle is actually being degraded. Whereas on the government level, this is good business for Peru.
So
So
privatization.
one
moves
witness
on.
is that history repeats itself, and we don't change.
I think human nature is really a problem. We've done very well with technology. I mean, we can do a lot of things, but if you think about how people behave, we haven't made a lot of progress.
One more question?
I understand Lonnie's working at ice or tropical glaciers around the world, but are there also similar socioeconomic and sediment studies occurring at others that you're seeing similar patterns?
Is it, just to understand this question, are there other socioeconomic issues in other parts of the, you're talking to these
Your
guys?
2 studies, and I'm probably not phrasing them correctly.
Are there similar, if I
Are there
understand-
similar work, the work that the 2 of you are doing, are these occurring at the other tropical glaciers, and are you seeing any similar patterns?
Well, for the tropical glaciers, we've drilled the Kilimanjaro in Africa. We've drilled the glaciers in New Guinea and the glaciers of the southern Himalayas. And the thing is that you see a very similar story. There's something that connects the tropics, and we think it's this high elevation temperature uniformity. But all these glaciers are retreating, and where we have maps, we can actually demonstrate the rate of ice loss is accelerating as you come up to the present. So yeah, it's a very, very similar story.
Yeah, and there are socioeconomic and water resource questions being researched in all of those areas. Well, we actually were in Kilimanjaro together, did a survey around half of the mountain to look at trying to age date to a first order what the waters in the big wells were coming from. And in Kilimanjaro, the ice doesn't contribute much at all to the current water because it's so small relative to the huge amount of rain that falls in the mid-flank of Kilimanjaro. But understanding how that might have changed through time is really kind of an interesting question. And other studies coming out of the Himalayas are actually actively revising how much the actual total mass of glaciers has changed. If anyone caught the news lately, there was an article that came out in Nature this past week, just published, about revisions to total mass loss based on gravity measurements from satellites, the GRACE mission. GRACE has a rather large and coarse resolution, but our best models would suggest that the numbers have to be revised downward quite a bit for the Himalayas. However, there's still a lot of interest in understanding just how the whole water cycle works. A lot of that water gets fed into groundwater at some level. So understanding those residence times are really key. So yes, and we ourselves are interested in that. We have some just preliminary work that's been done in that part of the world. There's a lot of lakes there too.
In what parts of the world do we still have, pure water? Is there any such a place where water is purer?
Antarctica would be the best.
Lake Vostok.
Yeah, Lake Vostok, they just drilled it.